My name is Aman Singh, and I am doing this workshop for Google Crowdsource Community on computer architecture. This series one of it. Oh, first, let's start with what is a computer. A computer is a machine where you can perform arithmetic and logic operation, and you can program it also. Therefore, uh, now we have two types of computer: classical computers and quantum computers. Quantum computers are those computers in which the basic units by which we store information or states, we can say, are 0 or 1. And in quantum computers, there's not 0 or 1. They can store uh, many qubits. Like it is a linear combination, like of vectors, you can say, of wave whose wave amplitude are alpha and beta, then alpha of 0 and alpha of 1. In terms of qubit, when we will study quantum computers, they are uh, they are explained differently. Then they are like many states. They are not like 0 or 1. There are many states. It can lie between. If you consider a circle hole, then for 0 1 you can consider it like it is a 0 degree, and you used to change it by 180-degree, then you will get the other one bit. But in quantum computers, there is like a whole circle. You can rotate 360-degree in the whole sphere. If you consider it, you can consider sphere if you consider them as vectors. For classical computers, logic gates, capacitor, transistors define the states of the bit. Like you can change the state of the bit by using these components in computer organization. uh, because logic gates are just like simple hardware which controls the bit. Like a NOT gate is there, you can change the if you input 0, then you'll get output as 1. Therefore, you can change the states of the bit. And now we should start with what is computer architecture. Computer architecture is also known as instruction set architecture. So it's just like a sequence of instruction that that a program performs to get the output. uh, and computer organization is like the implementation of ISA. We'll get more details by the when we'll study the examples ahead. Uh, we'll do the transformation hierarchy, history, basic operation of a computer, and the future that computer architecture withholds, and multi-core systems. Now the transformation hierarchy. For the transformation hierarchy, there's like a problem. You design algorithm for it. There are program language like Python, Java, many languages are there. There's a system software like virtual machine is there, operating system is there for which will connect the software hardware. Interface is computer architecture. Then we have microarchitecture, computer organization. Then logics are there. Then devices, electrons are the basics of building blocks. Therefore, the part which we have to study of this is uh, software hardware interface and microarchitecture. This belongs to the computer architecture zone. But we cannot create computer architecture without computer architecture designs, without studying the top level and the bottom level, because it connects. Therefore, it should be practically feasible also. We can send the transformation hierarchy with example like Morse code is there. If like if you consider the many centuries ago, many decades ago, if two people are there and they do not have phone and they want to communicate with each other, then they could use like flashlight on and off. Therefore, uh, if on and off there are two signals, therefore up if consider there are two buildings far off, and one person is giving the signal and other is applying algorithm to get the output of it. Therefore, if we come to the transformation hierarchy, is a problem. Like he will give the signals and we have to convert it into output. Therefore, we'll design algorithm like how we should do it. We can do it in two ways, like a tree method and a table which we can search and get the output. and then system software level means is there in between, but that's not important. We'll focus on computer architecture, software, hardware interface. Like if we have here we have like we'll take the inputs and we'll match it with the output, means the table, and then we'll get the output what it will give. Therefore the input can be 1 here, the input can be 2. If it will 2, then it'll go to this table. If the input is 3, then it'll go to the third table, and if the input is 4, then you'll go to the fourth table, and then it will check in those tables. Whereas in the second method, it is first taking input, then it is storing it, then it is going, it is taking another input, then it is branching to other, like a tree. And therefore here what is changed is like, I'm talking about instruction set architecture. Like uh, if uh, if you get like one here, input size is 1, can be 2, can be 3, can be 4. Here input size, you take one input, then you take one input, then you take one input. Therefore the, you can say the data size or data types in uh, uh, in computer architecture, instruction set architecture, these are described. And if you see it as like, if somebody interrupts, like if you are in room, if you are a child, and if a father interrupts you in between, then there is a priority order also. Like in the sequence, it will stop the execution, like you will stop and open the door. Therefore that thing is called as interrupt in between. And you have stored this data, therefore a memory is also needed, and the other person is giving you the input, and therefore input output, and you're storing the output in your brain. Therefore the output is there, and the whole process is carried out by your brain. Therefore the you can say microarchitecture is your brain only, most. Whereas the just the we are not talking about this area, mostly this area in this problem. And therefore then we move on to history. In history there are Pascaline, which is was used to solve, uh, that is add two numbers or subtract two numbers, was centuries ago. Babbage was there, in which it was first mechanical computing device. Then uh, ENIAC was there in 1945. Then IBM 360 was the first, like there at the time of 1960s, IBM 360 was released. Before that there was not much progress in the computer architecture field, where IBM 360 has laid the foundation of computer architecture in that. And here only one thing to important note is there, like transistor developed around IBM 360. Therefore we'll study Moore's law next. In that the number of transistors, as you can see, the Moore's law is the observation that the number of transistors in a dense integrated circuit doubles about every 2 years. First, it was a single year, but afterwards it was changed to 2 years. And you can see the 1970 is there. Then a type of linear graph, according to this, is uh, a table, y parameter. This has increased to 2005 only. This data is there. Therefore, it is around 18 months it is written, but around it was 2 years. Then we'll study the von Neumann architecture. In von Neumann architecture, we take we have to perform we have to solve a problem. Therefore, uh, we have certain units to solve to complete the problem. Like any one unit cannot solve everything. Therefore, to we differentiated like input devices there, like a person giving, which I said, like signals data, and output, like what is the number of the Morse code. Therefore output device is there, and the CPU is there. CPU contains control unit and ALU, arithmetic logic unit. Control unit is mostly like the operation, like the sequence of instruction. Like any instruction cannot be found anytime, like there should be an order. in which instructions should be formed. Like our data should be stored before it is operated, like something like that. It controls the signals, and arithmetic logic unit perform the operation like minus, plus, multiply, divide, and the the op- uh, here the memory unit contains both the data and the program, that is instructions. Therefore, it is called von Neumann architecture. The problem with it is that we cannot uh, access both the data and program at the same time. Therefore, by a single bus or data path. Whereas in a hardware architecture, it can happen. Therefore, the instruction, if at ALU is performed, there should be a instruction, the opcode is there, the operand is there, and the data is given to the arithmetic logic unit, and the instruction is executed, and the output is calculated by ALU, then it is sent to the memory unit. The calculation does not take place in memory unit because the clock cycles of ALU and memory unit differ. Therefore, then we have like machine was uh, by Alan Turing gave a theoretical model of a machine known as Turing machine. Therefore, he considered like two tapes of infinite length on both end, and then he considered this as a block. In that block, one set of symbols was there. Then any element should point it to that column or block, and then there should be a left, it can move left or right. Two operations are there, and we can generate an algorithm which can solve every problem which is there. It was a thesis, and after that a church during thesis, church also gave contribution to it, and then it became a thesis. Any real world computation can be translated into an equivalent computing involving a Turing machine. Therefore, if I have to explain it 1 minute, uh, go. Mm, If we take like 1 second, if we take like this is like a dollar sign, and this is also, I should have chosen free pen, freehand. Leave it. I'll show by this only. It is one. It is two. It is three, and it is four. Uh, and it is like nine. Consider it. Uh, the writing is bad, but just let's consider it. If this is there, and we have to add a one to this number, and therefore what we need is like we need to get the state, like uh, what is the previous state of this, and we'll add one to it. Like 9 is the number, and we add 1 to it, then it will be 10. I can't make a 0 probably, and we'll mod it by 10. Therefore, what will be the result? We'll save it in this register. Therefore, the result will be 0. I therefore the I type it only. Just leave it. Text. Therefore, a 0 will be the output of here, because here was 9 and here was like 1, 2, 3, 4. For column, I make it Just I'm adjusting it. Just a second. Oh, good enough. No, I just changed the values of this is too small. I changed this to 2, then this to 3, then this to 4. Therefore, this was there, and this was before as 9. Therefore, if I this 0, this 0. Therefore, if I here was a dollar sign, and if we add 1 to it, then it will become 0, and the carry which will attain it will go here, and we'll add 1 to it, then mod it by 5, then we'll get result as 5. Then we'll there's no carry, therefore it will be like uh, 3 3, it will be 2, and it will be 1. Therefore it is like this is a by this is a Turing machine which can solve any problem which is there, like it was presented in that way. uh, Therefore this thesis means it's not a theorem because it cannot be proved, it is always right, but a counterexample has not been picked up. Then we'll see what is the future that the computer architecture hold in today's society. Like we'll discuss this UPM, EM, then Tesla, MLX later. Tesla is developed, then Rho hammering problem, uh, meltdown inspector, UPM processing in RAM engine. Here in UPM processing, the processing when we have studied the Newman architecture. 1 second. Here, the data should be taken to the arithmetic logic unit, and then the output is calculated, then brought back to the memory unit, which requires a lot of power consumption and all. Whereas in UPM processing in RAM region, this doesn't occur. The processing takes place in the memory, but the processor is of low capacity than the external processor which we get, but it is much more less power consumption is there. Therefore, it works well in today's, because power consumption, like it saves you cost also. Therefore, it reduces the price also. Therefore, it is statistically financially very good. Then there is a Intel Optane persistent memory. Here we have like this memory doesn't it is based on 3x point principle. It doesn't lose memory. Like when you switch off the computer, your RAM loses memory. It doesn't. Therefore, if you have like you import, you make files, you store data, and then you work on it. Whereas when you have a non-volatile main memory, the you don't work on it. Like uh, you can store the data and it will be there. Therefore, you can gain it. It is around 128 GB. It is written. Therefore, it is not like less data. Therefore, you have to not make files and all. It is a different type of differently you will work on it. And also in like we have microarchitecture. Uh, Microarchitecture in this, like uh, uh, the ISA is there, and here is like we implement ISA. There are many trade-offs, like power is there. Like sometimes we want more, we want the processing power, then different types the chips are built, like and like into 86 is the same instruction set for both Intel AMD, but they work differently. Like therefore the implementation differs. Therefore many chips with the same instruction set differ, and there are trade-offs for it, like any chip has less memory, any chip has more memory. It depends on the purpose for which we are using that. Uh, and this uh, Intel Optane persistent memory comes with big and affordable memory, high performance storage, direct load storage, SS, native persistence, hardware. This all understandable. And the problem with it is like if your system contains like a bug or error, then when you open the system again, the bug persists. Whereas now in our system, like you just reboot it and the bug goes away. Therefore, it has its trade-offs are there. It has its ups and downs. Tesla ML accelerator. Tesla is like a car company. Like it used to build cars, but after this, like when it entered into self-driving cars, now to achieve the highest potential, they start developing chips, and therefore this is a Tesla chip for computer vision. Ma- Means machine learning can be applied easily. Therefore, it has two chips. The purpose of it is like it increases the cost because there are two chips, but redundancy is just like if this uh, bit flips are there, like anybody can there when we'll read the security of it afterwards in Rho Hammer, we'll see that bit flips are there and it can cause us to damage because it changes the hardware. Therefore, if two chips are there and they both perform the same operation, and if they both give the same output, then only the process continue. Otherwise, it's just like it doesn't continue. Therefore, you will know that error has occurred and something is wrong with the chips. Therefore, redundancy is very good because self-driving cars can lead to like that situation in the future. There's a row hammer problem. Row hammer problem. It it is just like when we study Newman architecture. Here here if I say the memory unit is considered of primary memory and secondary memory that is there, but it is a linear array of cells like a table is there. If I show one minute, a table only, just let me search. One minute, get a table. Ah, if I get it, it will be fine. Otherwise, I'll just say it is a linear array. Uh, Leave it. I'm not finding the table, and it is just like uh, it is just like a linear array. Like this box is there. Then if I draw a line here and I draw a line here, then it is a linear array of uh, address. It contains linear array of memory like 0 1 2, like memory address will be there which will be entered. Therefore we're discussing Rho hammer and this is like memory, and for memory when you assess it, like you there is like computer organization will study their capacitors which are used for storing data and all. Therefore when you provide a high voltage, then this memory is assessed, let's say, and then when you do not access this memory, then it will be V low. Therefore you are changing the voltage continuously of this cell only. Like if like this cell is you read this cell, then this cell, then this cell, then nothing will happen. But continuously if we read the same cell, then uh, as time passes, what happens, the nearby rows which are there, it has like its charge reduces by time. Therefore after many like when you have accessed this cell many times, then what will happen, this will discharge totally. Therefore it will change. Like if it was a high voltage, means it can contain charge, and then it would be 1, and if it doesn't contain charge, it would be 0. Therefore what you have done, you have changed the bit of the row without even assessing it. Like you've changed the data without even assessing it. Therefore it can cause huge problems. Therefore uh, it is like bit flips first point when Bitflips is same only this, and therefore the this was found in 2014. After that, up till now, we have not found a cost effective solution, let's say. And this was used by many hackers all throughout, like it more than 80% of your RAM chips have this vulnerability. Therefore, like anyone who is knowledgeable, like hackers and all, they can use it to access information, to hack your computer, to gain the root access, and that all. Accelerated GPUs was used to attack this. We can attack it over the network. Then neural network accuracy, like if a machine learning model is there, like 90 90% accurate, and then if you uh, Rho hammer it, like Rho hammering occurs, then the accuracy will drop to 10%, let's say. Therefore, uh, it will destroy your purpose, like for which you have built. Even he's not accessing the data. Like, okay, you have stopped accessing the data, but it can harm the system, and therefore, it leads. It is it is a very difficult issue which should be tackled, and we have come up with solutions like this row cell victim row cell aggressor is there. Then if what happens if we just refresh the rows, like this charge when it decreases, like it is decreasing like with time, not like sudden. Therefore, if we refresh the cell, if we refresh the charge of that cell before it reaches zero charge, therefore then what will happen is like the bit flip doesn't occur. Therefore, this problem, let's say, is solved. But the uh, when you refresh it, what happens, like the system consumes power. Therefore, and it's not cost effective, like you can refresh every row. Therefore, the solution which is used today is just like the probability of rows which is assessed, and the nearby uh, memory cells which are assessed will be the probability of that being refreshed will be more than any other. Therefore, it just reduce it. It is more cost effective. Uh, Therefore, this is all about Rho Hammer. Then we have Meltdown Inspector. The in Meltdown Inspector, like here, what will happen? You change the bit flips. Therefore, you cause something to the hardware. Like in this Meltdown Inspector, there's no hardware and software vulnerability. Like everything is working fine, but speculation execution is there. Or cache is like when you bring the memory when uh, when you bring data to the main memory, then what happens is like some data which can be used is also imported. Therefore, that is a work of a cache. uh, I I forgot to import a I have like in the multi-core models. uh, yeah, there this is like core one core one, then it is the cache of this, and this is core two, this is the cache of this. These are separate caches for separate rows. uh, Therefore, in this main memory, what happens is like there's a it when cache is uh, used, then it leaves a data track of data. Therefore, the other person like hackers could use that data path to get other data which they don't have access to. Like here, what happens is like cache data, it has not been required by the program, but the data has been brought. Therefore, if a hacker uh, introduces a malware into your computer which make that specific data which is like root assets, or which cannot be gained by normal user, to follow that track path, and then you can uh, gain that data from the cache and then use that data. Therefore, it has issues. like hacking. Therefore it needs to be solved. It is like just like many into like they introduce patches of this to solve this problem. Then there are like multi-core chips, like this uh, core core one, then cache is there, then core 2, cache is there, core 3, core 4. The by mistake the data isn't copied, like I have to change this. One, I just deleted better. This is there, multi-core chips. And this chips, like we assume, like if you add more number of chips, the performance will definitely increase by that much time. Like if you get work done in 2 days, then if you introduce by one chip, then if you introduce two chips, then you will get the work done in one day, something like that. But this doesn't happen because of memory performance hog. There when this was a experiment, like we ran to process MATLAB and GCC in the same system, and then what happened is just like there's a high performance was given to GCC and low priority was given to uh, uh, MATLAB. And just like here, MATLAB, you can see MATLAB is uh, I- mm, just MATLAB is uh, MATLAB is giving more instruction. Like these two caches are different. MATLAB is giving more. It is accessing more RAM memory continuously. Therefore, when a GCC uh, gives instruction, it does not get executed here because like the the slowdown in MATLAB is less because uh, the data it is accessing the memory more frequently. Therefore, the GC cannot pass through it. It is accessing memory from the core one only. Uh, Therefore, and it is not a OS problem also because we have changed the priorities of this to MATLAB and GCC, and nothing changes, and it is not caused by thermal. Also, it is not caused by thermal. Like one core is heated and the other core is not heated. Therefore, it causes these issues. This was also not the problem because it's too random because they were on no they were the same temperature around when the experiment was conducted. Therefore, and this will be the end of the workshop. Like this, this is references I've taken from Onamutlu sir and Smruti Ranjan Sanghi. You can find these lectures on YouTube, and there is a book called Charles Pedler Hidden Language of Software and Architecture. And that's all. Thank you. Hope you liked. Yeah, Vishwas, it's where it's done. Stop.
Yeah, I know you're a fresher to the game.
But yeah, I thought like I went fast. I don't know where. I went slow. I don't know where. Just like
Fine, fine, fine.
when.
You are in live now. Don't worry about it. You have actually given an opportunity, and you have actually killed it, dude. Don't worry. You are still in the first year. Actually, second year. Don't worry. First year
Yeah,
was just like
yeah.
just given to
First year
you.
was the quarantine and all. Nothing
Don't worry
happened.
about it. Everything was awesome. Like, don't worry. You want 10 more? I can get the slots from those guys. I can get the meetup thing done. Don't worry. You are good to go. Don't worry. Everything is
Yeah, but
fine. And trust me.
my only objective was like no to not focus too much on technical details in the first workshop and get to know like which industry works. Like okay, Tesla is working, which is a car company, and then
Mhm.
Rho Hammer problem is there. Therefore, before that, security experts were not involved in computer architecture. Therefore, now they are involved more in. Therefore, this industry is booming right now. And then there is a quantum that's why I've introduced quantum computer in the starting, because if for develop in the future, quantum architecture will take place. You have to develop it, and therefore you should know the basics of what before it's developed. And in the 10 years, like, quantum is the future. Like,
Yeah, that's
every
good.
big company is working on it. Like, and there's like problems like Spectre also, problem is not solved. Like, no, there's no like, we are reducing the chips to smaller
Yeah,
levels, which has caused Rho Hammer problem. Like, before 2000, Rho Hammer problem doesn't exist, but 2012 to 2013, average chip which was released had Rho Hammer problem, like 100%.
yeah.
Therefore,
It still prevails and it still is there because technologies are shrinking, but yet we are making some new changes up there.
yeah. And
Maybe one
like,
day we will, yeah.
where
Maybe
like, no,
and we'll end the broadcast here. We will
yeah,
have the after webinar discussions in the phone. Don't worry. If you
yeah,
have any
okay,
doubts, reach out to me. That WhatsApp group is open. You can ask any doubts and you can really go on. Or else my LinkedIn is still open. Ping me up there. I'll reach out to you back. Thank you, folks. Thank
yeah,
you.
thank you.